The leading explanation for this astronomical oddity centers on what planetary scientists call the giant impact hypothesis, a cataclysmic collision that would dwarf most cosmic events in our solar system's history. This cosmic collision represents a pivotal moment in Venus's history, a singular event that transformed the planet's fundamental motion and set it on a different evolutionary path from Earth. According to this theory, a massive celestial body, perhaps a protoplanet or large asteroid, slammed into Venus during the solar system's formative years. The collision was of extraordinary magnitude, powerful enough to fundamentally alter the rotational momentum of an entire planet. Computer models suggest this impact would have delivered approximately 1.64 times 10 superscript 3 superscript 1 joules of kinetic energy, transferring an angular momentum of about 1.99 times 10 superscript 3 kgm superscript 2/s, figures that represent almost unimaginable cosmic violence. To comprehend the precision required for such an event, we must understand the physics of planetary rotation. Any object striking Venus would need to hit at precisely the right angle and with sufficient force to overcome the planet's existing rotational momentum. Think of it like hitting a spinning top. You need to strike at exactly the right spot and angle to reverse its direction. Simply hitting it anywhere won't change its spin direction. The impact must apply torque in the perfect way to first stop the existing rotation and then impart new momentum in the opposite direction. This scenario bears some resemblance to the impact theory of our moon's formation, where Mars-sized object called Theia collided with early Earth. However, Venus's collision would have needed to transfer enormous angular momentum directly to the planet itself, completely reversing its rotational direction rather than primarily ejecting debris. Computer simulations have been particularly revealing about the specifics of such an event. Models suggest the impactor might have been a proto-Mercury-sized object that struck Venus at a shallow angle. Interestingly, some scenarios indicate that if the collision was grazing enough, a significant portion of the impactor could have escaped Venus's gravity after transferring its momentum. This raises a fascinating possibility. The object that reversed Venus's spin might have reformed into what we now recognize as the planet Mercury. Other simulations suggest alternative fates for the impact debris. Some material might have been captured by the sun's gravity, falling into our star over time. Other fragments could have contributed to Venus's already substantial atmosphere, potentially explaining some of its unusual atmospheric properties compared to Earth. Timing plays a crucial role in this hypothesis. Most planetary scientists place this theoretical collision within the first billion years of our solar system's formation, during what's called the late heavy bombardment period. This era, roughly 4.1 to 3.8 billion years ago, saw intense asteroid activity throughout the inner solar system as gravitational interactions with the giant planets sent countless objects on collision courses with the inner planets. During this chaotic period, impacts were common, though few would have been large enough to alter a planet's rotation. The specific impact that potentially reversed Venus's spin would have been exceptional even by the standards of this violent era. The precise mechanics would have required an object with both substantial mass and the perfect trajectory to deliver its angular momentum efficiently to Venus. One of the most significant challenges to the impact hypothesis is the conspicuous absence of evidence. Unlike the Moon with its visible impact basins or Earth with its geological scars, Venus shows no obvious surface signs of such a catastrophic collision. This absence presents a significant puzzle for scientists. Where is the evidence of an impact powerful enough to reverse a planet's rotation? The answer likely lies in Venus's unique geological history. Unlike Earth, Venus appears to have undergone a global resurfacing event approximately 500 million years ago. This dramatic episode effectively repaved the entire planetary surface, erasing any visible evidence of ancient impacts. The planet's extreme surface conditions, hot enough to melt lead, combined with its active volcanic processes, would have obliterated any impact basins that might once have existed. Furthermore, Venus's dense atmosphere makes studying its surface challenging. The thick clouds of sulfuric acid obscure direct visual observation, requiring radar mapping to see the surface at all. These practical limitations have hindered scientists' ability to search for subtle evidence that might support the impact hypothesis. Despite these challenges, the impact theory receives support from several aspects of Venus's current state. The extreme tilt of Venus's rotational axis, which has the planet spinning nearly upside down compared to most planets, aligns with what we would expect from a massive collision. Additionally, Venus's remarkably slow rotation rate makes sense in this context. A glancing impact would have imparted residual angular momentum that gradually slowed over billions of years. For the impact hypothesis to hold true, scientists must determine precisely what type of collision could achieve the necessary rotational change. The angle would have been critical, too direct, and the impact might have shattered the planet rather than changing its spin. Too shallow and insufficient momentum would have transferred. Computer models suggest the impact would have needed to strike an angle between 10 and 30 degrees from horizontal to achieve the right balance of energy transfer and planetary stability. The giant impact hypothesis remains the most scientifically compelling explanation for Venus's retrograde rotation, but it's not the only theory scientists have proposed. Alternative explanations include complex gravitational interactions with the Sun and other planets, or unique atmospheric tidal coupling mechanisms that could have gradually altered Venus's rotation over billions of years. The tidal locking hypothesis. Those atmospheric tidal coupling mechanisms scientists propose aren't just technical jargon. They represent a cosmic tug-of-war that Venus is currently losing. The Sun pulls one way, Venus's atmosphere pushes another, and caught between these massive forces is a planet whose rotation defies our understanding of how solar systems should behave. The interplay between a planet and its star creates a phenomenon known as tidal locking. When a celestial body becomes tidally locked, it always presents the same face to its parent star, much like our moon always shows the same side to Earth. This occurs because the gravitational pull of the larger body creates a bulge in the smaller body, and over time, this tidal force slows the rotation until one side permanently faces the source of that gravitational pull. For planets close to their stars, like Venus, the Sun's gravitational influence exerts tremendous force. Venus should have become tidally locked billions of years ago, with one hemisphere perpetually facing the scorching sun and the other in darkness. Yet something intervened, something powerful enough to prevent tidal locking and push Venus into a backward spin. The answer appears to lie in Venus's extraordinary atmosphere, a dense, turbulent system that actively engages with the planet rather than passively surrounding it. Stephen Kane, an astrophysicist at the University of California, Riverside, offers a crucial insight that reshapes our understanding of Venus's